The topic of my today's talk would be classical limits of associative algebras. So the goal to reproduce classical physics. And I will consider two main examples. First example would be algebra of differential operators. And second example would be high-spin systems as classical limit. The inverse spin 1 over j would be a Planck constant. And we will try to get specifically. We are aiming at the formula df over dt is hf, where f and h are functions on the phase space, where pi ij is so-called Poissonian bivector. Pi ij is omega minus 1 ij, where omega is a symplectic form, because this is classical mechanics. So how are we planning to get there? Through examples. Algebra of differential operators. Elements are, so let us start with one variable. Elements are ak of x, d over dx to the power k, and here we take a sum up to n. It is clear that product of differential operator is a differential operator. Suppose we start with this one and with this one. We just need to take derivatives from the left to the right, and as a result, we will get something like plus something d over dx to the power k plus l minus 1 plus etc. However, it is just an algebra. We need a family of algebras. So we will make a modification that I'll call differential operators labeled by H. And its elements are these sums. What is interesting in this modification? Consider commutation of two elements, commutator. So first term is something like this. So we just multiply and we have the leading term. However, we have an extra term. And extra term comes when we differentiate with this d over dxk the function bl that stands here. So it will be h to the power k, h to the power l. So we are taking this derivative to the right, and we have actually k ways to differentiate this poor bl of k. Minus 1 plus higher terms. Now, there are several terms. Term number 1, term number 2, and there are also higher terms. Term 1 is just like multiplication of polynomials. So when we multiply polynomials, we get exactly this expression, and it is commutative. Let us have a look at term 2. Put it in a standard form in, how did I call it, in DAH. The derivative here has degree k plus l minus 1, and here we have just k plus l. So second term has the form h, and here we have an proper element from the DAH. Clearly, the terms that I denote like several dots are h squared by something plus h cubed by something, etc. Result of the exercise. Commutator of elements from DAH is the following. To an element alpha that belongs to DAH, we correspond its symbol as alpha. That is a polynomial in P. So these are the functions on the phase space phi with coordinates x and P. Now, commutator alpha beta equals h times something that I call c of alpha beta plus h squared times something that I'm not very interested in. What we know about this c? Symbol of c alpha beta is nothing but d alpha over dp d beta over dx minus d alpha over dx d beta over dp. It is a Poissonian bracket on the space of functions of x and p for omega that equals dp dx. This is a classical, actually quasi-classical limit of a commutator. Another way to look at DAH is to say that it is generated by function of x and operators h d over dx. Now we will consider another example. Example above is used in 99% of books. Now we consider the equally important example studied in 95%, in 5% of books. Consider the vector space of polynomials of degree n in two variables, z0 and z1. So it is known as sections of the bundle On on CP1. It has dimension n plus 1. So this space is z0 to the power n. Consider homogeneous differential operators of the form, 4 of them, since I, j could be 0 or 1. I put here the letter Vn. One of them, it's called Euler operator, acts in a non-interesting way. I acting on Vn is n acting on Vn. Other are interesting. They form an SL2 algebra. We will call it T3, T plus, and T minus. T plus rises the degree of Z1 by 1, T minus lowers by 1, T3 computes the difference. Interestingly enough, we would like to make V a Hermitian vector space. So we need a metric on the space of polynomials. We will use the following metric. So we need this integral to be convergent. It's really a Hermitian metric. And one may check that d over dzi applied to P goes by integration by parts into zi P1, P2. How does it happen? Say for z0. We integrate by parts, minus. So if we take derivative here, we have a minus, so we need to add. Now this term goes to 0 since P1 bar is holomorphic. Sorry, here I have Z0 bar, and so this gives me Z0 P1 bar. In this way, I have proved this main assertion. Thus, Z1 d over dz1 minus Z0 over dz0 is Hermitian, while T plus Hermitian conjugation is T minus. In this way, I see that Hermitian operators are T3, and then there will be operators that I'll call by their standard names. T1 is T plus T minus, and T2, that is IT plus minus T minus. And here I am going to make a break, but before the break, I'd like to ask for questions.
What's the motivation to define the inner product?
What's the motivation to define an inner product? The motivation to define an inner product is to construct the quantum mechanics. And quantum mechanics was a Hermitian vector space with where Hermitian operators played specific role. They were observable. They were corresponding to physical quantities that we observe. In particular, their eigenvalues were numbers that we were getting out of the experimental devices.
Can you remind me where the exponential of z squared come from?
The exponential of z squared, okay, was coming when I was trying to define a Hermitian product. You see, I have two polynomials. The question is, how can I get a number out of them? I would like to integrate something, but I need to integrate it with some measure. I cannot integrate with this measure. Integral will be divergent. So I used this exponential to make it convergent. Of course, it is a choice, but I would prefer to have this choice. You may consider it as a piece of a construction. So altogether, I constructed n plus 1 dimensional space of polynomials that have the following inner product and that have, besides this inner product, an interesting class of Hermitian operators, namely these operators. They are not the only operators that we have in this system. Other operators, other Hermitian operators, could be constructed by multiplying Hermitian operators of this type. So, let me give an example for an example. For n equals to 1, V is just a span of Z0, Z1, and operators T3 is 1, 0, 0, minus 1, T plus is like this, T minus is like this, then T1 is like this, T2 is like this. This set of Hermitian operators is called Pauli matrices in the literature. However, we may consider the space V2, and here we have 3 by 3 matrices. In particular, T plus would be something like this, T minus would be something like this. However, there are other operators like T plus square, T minus square, and even Hermitian operators like T plus square plus T minus square. Okay, now we will have a 10 minutes break. Let me continue. It is instructive to compute commutators of T matrices. In particular, compute commutator of this. So here I will have 1, 0, 0, 0 from this term. And similarly, I will get minus 1, minus 1, 0, 0. So it will give me 2t plus. In this way, I will get that T3 T plus minus equals 2t plus minus.
No, it's supposed to be plus minus 2t plus minus.
Yes, of course. Thank you. And similarly, I can compute t plus t minus. So I will not go to do this computation. It would be twice times the algebra of SO3. So in terms of Ti, I will get Ti Tj would be equals to epsilon ijk Tk. And here I'll have this too.
Wait, are you sure about this? Because the commutator of t plus and t minus is just t3 without a 2. So it is just SL2, which is which after change of the basis becomes just regular SO3.
Okay, so
Isn't it?
let
Without
us
a 2.
let us see how it works. So let me see the number here. So you see here I have 2 standing here in front. That's why. Okay, so maybe it will be instructive to make corresponding rescaling. So let us compute. So I think you are right. Is actually T3. So here I have T3. So how can I get? Then the question is, how can I get the standard form of SO3?
But it's fine. It does obey the regular commutative relations for SO3. That 2 is not needed. If T1 and T2 are connected with T plus and T minus, as you've written above, then it's fine.
So how do I get this 2 here? I mean here.
Well, it just happens naturally. There's no need for rescaling. It's a this 2 is normal for SL2.
Okay, okay. So let me.
Can you show the definition of T plus and T minus in terms of T1 and T2 again?
So maybe so these were T plus and T minus, and these were T1 and T2. Okay, for T1 and T2.
Yes, and T plus and T minus are defined as T plus is T1 plus what is it?
Okay,
Oh, and by the way,
my...
T2 should be 0 minus I 0.
Okay, so let us take this definition, yes.
And then T plus is T1 plus I T2 over 2. And T minus is T1 plus minus I T2 over 2. And this change of basis reproduces the regular SO3 algebra.
Yes, so where did I made? So did I made any kind of mistake?
Can you scroll a bit further up? Well, here everything is fine except for the sign in front of T2. T2 should be minus I.
Okay.
And then but everything else is correct. It's all fine.
Okay, so it means that there is no coefficient of 2 here. Okay.
But there should be an I.
Yes. So actually, in order not to mix conventions, I will put here A, B. Of course, there should be an I here, and here I should write A, B, C, D, C. Okay, and I do not need it. Well, thank you. So up to now, I have these T operators acting on Vn, and Vn is a representation of actually SU2.
I have another question. If you scroll up a little bit, and what about these T plus and T minuses in 3x3 matrices? If we take T plus and T minus to be defined in the same way as above,
yes,
through T1 and T2, which are matrices in a corresponding representation.
Maybe there are 2.
Then T plus and T minus, they don't look like this, I think.
Yes, there is something like coefficient like 2. Okay, I wrote approximately. It is because, okay, let me compute it. So let us do the computation. Z naught square, Z naught Z1, Z1 square. So T plus was Z1 D over DZ0. Yes, T plus applied to Z naught square was 2. Thank you. Z naught Z1. T plus applied to Z naught Z1 was Z1 square. So actually, there is a coefficient 2 standing here. And similarly, there should be a coefficient 2 standing here. So altogether, it means that there is coefficient like 2 standing here. So it was not exactly the form of these matrices that I was going to show. I wanted to show that t plus square and t minus square are different from t plus t minuses. So they have matrix elements far away from diagonal. Okay, so after all, you made this computation. Now, once again, Vn is a representation of SU2. The lowest eigenvalue of T3 was or is minus n. By convention, it is called 2J. So physicists, where J is called a spin of the representation.
Wait, why is it 2J?
Example, maybe 2J plus 1, no. Example, Vn, V1 contains the span of Z0, Z0, and Z1. N equals 1, J equals 1/2. V2, N equals 2, J equals 1. Okay? The dimension of Vn is clearly n plus 1. And in this convention, dimension of Vn is 2J plus 1. Tim, do you agree?
Yeah,
Okay, so people call this spin of representation because originally people considered only representations of SO3, not SU2. And these were representations for even n, like V2 was three-dimensional, and it was called vector of SO3. V4 was correspondingly five-dimensional, and so on. So five-dimensional representations, okay, let me make this comment, was considered like this. People studied symmetric product of representation, so these were symmetric matrices, MAB. So A was running from 1 to 3, and B was also going 1 to 3. So altogether, the number of matrix elements was 3 times 4 over 2, so it was 6. However, trace of MAB was SO3 invariant. Sorry, not MAB, trace of M. So representation was five-dimensional. In terms of SU2 representation, it corresponds to even n. Okay, now what I would like to start to do is to change the algebra, but in a simple fashion. I will go from T to what I call T classical. That would be T over n. In particular, eigenvalues of T3 in Vn were minus n, low dots, to plus n. Eigenvalues of T3 classical would be minus 1 to 1. However, there will be n plus 1 values. 2, 3, n. And in this way, T3 classical somehow tends to what we may call a coordinate on an interval, whose eigenvalues are a segment. So here the spacing is like 1 over n. Now, it is clearly that commutator between TA classical and TB classical was I epsilon IB ABC TC classical, and here there is very important 1 over n. So when n is going to infinity, we were approaching commutative algebra. So we need to study first thing, the spectrum of corresponding commutative algebra, and second, the Poissonian structure on this spectrum. So let us study the issue 1. There is a well-known formula for so-called quadratic Casimir operator on Vn. Quadratic Casimir operator C is T1 square plus T2 square plus T3 square. It commutes with all TAs. So you may expect that it is a scalar, here just a multiplication by number. At the same time, it is a differential operator of order not greater than 2. So there is a technical exercise to get C in terms of Euler vector field and E, and then substitute by N. I will not do this computation. J plus 1. I am not sure about this number. This could be 2, but it's not very important. What is important is for TAC, that are TA over N, it goes like 1 plus O1 over N. So while, sorry, not while, so in the limit N going to infinity, TA become commuting variables XA with the relation TAC. And this is exactly a sphere S2 in R3. Now we may compute the first term in 1 over n in the commutator and see that is 1 over n epsilon ABC. This implies the following. Consider the algebra A n, let me put here C, generated by TAC, acting on the given vector space.
I'm sorry, in what meaning is this in algebra? We take some vector and we act by these generators and we get some other vectors? Isn't it just a vector space?
When I say algebra generated by generators, I mean the following. I mean that we consider words TA1, C, TANC. And here I have some symbols, alpha A1, alpha AN. So this is an element of A and C.
So a universal cover?
Yes. So it is universal covering algebra with C modification. So this algebra AN acts on Vn. So it means that I do not study all operators acting on Vn. I study only operators generated by TAC. You may ask what is the difference? Is N dependent?
You mean that those coefficients alpha should be n independent?
Yes, either n independent or go as 1 over n to some power k. Otherwise, it would not form an algebra. I need to be able to multiply two objects of this type and to get an object of the same type. However, commutation relations between t depend on n. Then alpha would correspond to functions on S2. Actually, not complex. Then Hermitian alpha would correspond to functions on S2. Actually, R, x1, x2, x3, and here is a relation. Ideal generated by x1 square plus x2 square plus x3 square equal to 1. Okay, minus 1. And I may consider commutator. And this commutator would go as 1 over n, I, and what would happen, what would stand here would be the Poissonian bracket, where Poissonian bracket on alpha beta would be given by d alpha over dx I d beta over dx a b epsilon a b c x c. And this Poissonian bivector of the form xa xb, okay, I'll write it differently, for f a b c being a structure constant of a simple Lie algebra is known as a Kirillov-Poisson bracket. And in this particular example, we have it for SO3 or SU2, for SU2. And here I will present without a proof statement that symplectic form corresponding to this Poissonian bracket is a round Fubini-Studi 2 form that people know as dz bar, where S square is C and infinity, and Z is a standard coordinate on C. That's why the system that I described, system of Vn and operators acting there, is known also as a fuzzy sphere. Okay, and I will continue with fuzzy sphere next time. I will discuss more about classical limit in the case of fuzzy sphere. We would like to know something about points on a sphere. Okay.
I have a question.
Yes, please.
So here we did a computationally at least a rather simple thing. We divided everything, we'll rescaled every generator the same way, and in the classical limit we'll get a somewhat simpler Lie algebra. But in general, we can rescale generators like independently, or rather by different factors, and get possibly a plethora of different algebras, right? Like we can rescale, I don't know, one operator or a couple of operators. If maybe not in the case of SO3, but in the case of a different algebra. So is there like a lot of room for experimentation, or?
It's a good question. I never studied it, but the question would be, okay, I don't know, honestly. So you may ask if it's possible to get other interesting Poissonian structures. So clearly, in general, there should be different Poissonian structures. This Poissonian structure is the Poissonian structure that preserves rotational symmetry. So proper answer would be maybe there is a room for experiment.